Hello students, welcome back, and let's go to section 4, partial derivatives and antiderivatives. This is from Calculus 3 or multivariable calculus. Some students took it, some students didn't. We'll have to do it anyway. Now, for the student who didn't take Calculus 3 yet, it's co-requisite. We're going to review as we go on, whenever Calculus 3 topic becomes necessary. And partial derivatives here is one of the topics that show up relatively early, so let's do it here. And it's easy. Theoretically, it can go deep, but computationally it's not too bad. What is a partial derivative? It's a derivative computation with respect to a certain variable, say x or y or z, regarding the other characters as constants. Those are partial derivatives. And how do we denote partial derivatives? Well, the total derivative, the usual derivative, we write kind of like this, du dx with d. Let me expand the font a bit further. This kind of thing is a derivative if you have u prime of x. But that's when you have just one variable. What if you have more than one variable? Then we do not use this notation to avoid confusion. We use these rounded d in place of this, the usual d. This kind of expression is used for partial derivatives. So let's calculate it. This is my function, right? Let's calculate the partial derivative with respect to x, leaving the other characters as just constant. Okay, let's take the derivative of x squared times y. Do we have to use product rule? No, it's not product rule. This is not implicit differentiation. Y is just a coefficient. The only thing that matters is x squared here. So 2x times y, this coefficient. How about this part? Y cubed is just coefficient. Stay there. And derivative of exponential function. Exponential always stays the same. Oop. Exponential always stays the same. And then by chain rule, we have to multiply the derivative of the inside. What's the derivative of the inside here? What's the derivative of x? That's 1. And what's the derivative of 2z? Is it 2? No, it's 0 because the variable is x. As far as x is concerned, z is constant. So this is 2xy plus y cubed times this exponential. Also, we use this kind of notation. Oops. U sub x. This notation and that notation are equivalent. Sometimes we use this notation as well. This expression, that expression, those expressions, they're all the same. I'm not going to use this expression very often, although this expression is accepted by Mathematica, so sometimes I do use it whenever I use Mathematica notebook, but otherwise I will not use it. I don't want to add confusion. But these two I'm going to use equally as often. Our textbook author prefers to use this one, I think. Okay, how about the other derivative computation? Okay, all right. And that is equivalent to u sub y. Let me expand the font a little bit further. Okay. All right. This is my function, and I'm taking the derivative with respect to y. So what's the derivative of this? Do I have to take the derivative of x squared in 2x? No, x is constant. It's just coefficient. It stays there. And the derivative of y is just 1, so it stays here. Next, exponential. And there's no y expression there, just x and z, so this is just constant. So constant times y cubed, so this is just coefficient. So the derivative is 3y squared, and then times exponential. So that is a derivative by y. So this is a derivative by x, that's a derivative by y. Okay, let's do derivative by z. Let's expand the font. And what's the derivative of this by z? This is constant, so that's 0. Now what's the derivative of this? Y cubed is just coefficient. You see, if this y cubed plus, then that'll go down. But times, so it's a coefficient. Y cubed plus something, then go down to 0. That's constant. But y cubed times, so that's coefficient. Now as for the exponential function, exponential always stay the same. And by chain rule, you have to multiply the derivative of the inside. Derivative of x is, what's the derivative of x? That's 0, because my function here is z. And the derivative of 2z is 2. So what do you get? We get 2y cubed times this exponential. So those are the partial derivatives. Let's see, did I do these right? Yes, they all check out. Now, how about some second derivative computations? Same functions here. And then what is this expression? This is equivalent to this, actually. So d times u, that's numerator, and dx times dx. Or equivalently, you write that u sub xx. Take the derivative by x, and then to take the derivative by x again. So let's go ahead and do that. Let's take the derivative by x. So take the derivative by x. Wait a minute, we already did it. It's here. So let's just copy and paste and use it. Okay, the green part, this one is derivative by x. And now let's take the derivative by x again. So derivative by x again, what do you get? 2y, right? Y is just coefficient. X goes down to 1. How about this one? Y cubed times this, so this is coefficient. Y cubed stay the same. And exponential always stays the same. And then by chain rule, we have to multiply the derivative of the inside. What is it? 1 plus 0. Derivative of x is 1, and the derivative of 2z, that's 0. So times 1, I don't have to write it. So that is a derivative computation, or that's the second derivative. Well, okay, that was one of the easier ones because I have to calculate the derivative with respect to one character twice. Here's a bit harder example. And it's actually this. We have to do this. So du, that's d squared u in numerator, dx times dy, so it's this computation. But u is here, so I have to calculate this one first, which is a derivative by y. So we have to calculate this one, derivative by y. So this function, and let's take the derivative with respect to y. But we already did it. It's here. So we took the derivative by y first, and then now let's take the derivative with respect to x. Derivative of x squared, that's 2x. How about this? 3y squared plus something, then that 3y squared will become constant. It's just going away to 0, but this is multiplication, so this is not constant, this is coefficient. 3y squared stay the same. Exponential, upon taking the derivative, exponential always stay the same, and by chain rule we have to multiply the derivative of the inside. What's the derivative of x plus 2z? Derivative of x is 1, derivative of z is actually 0 because derivative is done with respect to x only. So multiplying by 1 doesn't change anything, and there goes the derivative computation. Now how about the other derivative? This one is actually the other way around. We have to take the derivative by x first. And then we have to take the derivative by y. So let's go here and then take the derivative with respect to x. But I guess we already did it. It's here, so let's recycle that. So look at the red part. We took the derivative by x, and then now let's take the derivative by y. Okay, what's the derivative of 2xy? It's 2x. Coefficient and the derivative of y is 1. And how about this? This is coefficient, exponential stay the same. And then times the derivative of y cubed, what is it? 3y squared, isn't it? Did I do this right? Exponential stay the same, not because it's exponential, but because this is coefficient. And y cubed became 3y squared. Did I do this right? Let's compare these two. They're the same. So taking the derivative by y first and then x later, or x first and y later, made no difference. So take the derivative by y first and then x later, or take the derivative by x first and y later, made no difference. These two are the same. And are they always the same? Most of the time they're the same. As a matter of fact, students who took Calculus 3 will remember, whenever all the partial derivatives exist and they're continuous, then we can switch the order. It's Clairaut's theorem, or it's an example of Fubini's theorem, and never mind, the names are not that important. When you have some really exceptional situation that derivatives exist, but they're not continuous at some point, then we can create some counterexamples, but otherwise, things are going to be okay. Here in differential equations, most of the time, I take it back, every single time, we're going to be considering infinitely differentiable functions. So we don't really have to worry about these kind of things. So we can switch the order of derivative. X first or y later, or y first or x later. No difference. Look at this. U sub yx, y first, x later, and dd notation, d squared u, dx, dy. You have this switching here. So they can be really horrendous. But luckily, you don't have to worry about these. They're going to be the same anyway. Okay, so much for the partial derivatives and second order partial derivatives, and let's talk about integration. Now let's consider these kind of examples. We have partial derivatives, u is unknown, and partial derivatives are given, and we want to find out this u. How do I do that? When the derivative is known and we want to find out the original function, we simply take the antiderivative. We integrate it. Let's do the same thing here. U of x comma y is gonna be integral of u sub x of dx. And what is u sub x? It's given here. Come on. And let's calculate this antiderivative, all right? Okay, what is the antiderivative of 3x squared times y? This y is just coefficient, okay? So I can bring it out just like I bring out 3. So antiderivative of this, x cubed over 3. So we have x cubed and then y. And you can always check with partial differentiation. Take the derivative with respect to x, leaving y as constant, you get this. It's an easy exercise. Let's put some more space between. And then this is 2x squared, isn't it? Okay, antiderivative for it. Yeah, that's right. And plus, and then you're going to get an arbitrary constant. But this is not really a constant. Because if this had any y expression in there, upon taking the partial derivative by x, it's going to disappear anyway. So it should be, as a matter of fact, a function of y. That's something to be determined later. Likewise, let's calculate the antiderivative using this one. And here's my function. Alright, now let's take the antiderivative with respect to y. What's the antiderivative of x cubed? Is it 1/4 x to the 4th power? No, it's not. X cubed is constant here. So this is, as a matter of fact, x cubed y. How about this one? That's easy. 4y cubed. And now this is going to be tricky. You may have to use integration by substitute. Derivative of cosine is negative sign, so this is what you're going to need. And likewise, you're going to get a function of x. And then you can compare these two. Do you see x cubed y is common? That looks good. And here is expression of x alone. And these two are y alone. So comparing these, you're going to get this x cubed y minus 4y cubed plus cosine of y squared plus 2x squared. This time really plus c, constant c. Does everything make sense? This is partial antidifferentiation.